The James Webb Space Telescope, hailed as the most advanced observational tool ever created by humanity, has delivered a groundbreaking view of the red supergiant star Betelgeuse. This image transcends the realm of mere astronomy photography. It holds the power to fundamentally alter our understanding of how massive stars live and die. Betelgeuse, long a favorite among astronomers and casual observers alike, has intrigued many with its immense size, over 1,400 times larger than the Sun, and its vivid red glow. Positioned within the well-known constellation, Orion, the star has stood as a cosmic lighthouse, beaming its light across hundreds of light-years to reach Earth. However, Betelgeuse began exhibiting unusual behavior in recent years. Once one of the most consistently bright stars in the night sky, it suddenly dimmed, alarming scientists and stargazers. This dramatic shift triggered widespread speculation. Was the star approaching its explosive end in a spectacular supernova? Such an event would be the first of its kind visible from Earth in modern times, making it a historic astronomical phenomenon. But just as abruptly as it had dimmed, Betelgeuse's brightness stabilized, deepening the mystery and raising more questions than answers. Was this merely an elaborate celestial misdirection, or had our understanding of the signs leading to stellar death been flawed? The James Webb Space Telescope entered the scene as a technological marvel, equipped to look deeper into space and uncover details invisible to traditional instruments like the Hubble. Its infrared sensors can penetrate the cosmic dust that obscures distant phenomena. Recognizing the significance of Betelgeuse's erratic behavior, Webb made the star a top observational priority. When its first high-resolution images arrived, they astounded the scientific community. Contrary to the expectation of a star nearing its end, Betelgeuse appeared full of life and activity. Large, bright patches were seen dotting its surface, likely caused by powerful convective processes within the star. Its outer layer seethed with turbulence, resembling a churning, fiery ocean, far from the cooling, fading shell anticipated in dying stars. These observations challenged long-standing astrophysical theories. Conventional wisdom held that a supernova-bound star would undergo a gradual, predictable decline characterized by outer cooling and inner instability. Webb's imagery, however, revealed a much more chaotic and active surface, contradicting those assumptions. Surrounding Betelgeuse was an elaborate cloud of gas and dust, material violently expelled over time. These massive ejections have shaped the surrounding space into intricate formations, further complicating scientists' understanding of the star's current phase. Could this be a precursor to collapse, or might it represent an overlooked stage in a red supergiant's life cycle? This question has become a focal point in the study of stellar evolution. Scientists are particularly intrigued by the localized hot regions on Betelgeuse's surface, possibly caused by massive convective cells or previously unknown processes. Their presence implies that the outer layers of such stars may behave in ways not yet fully grasped. These new findings cast doubt on the established narrative that massive stars follow a linear path toward destruction, one of steady dimming, increasing instability, and sudden collapse. Webb's data suggests a far more erratic and complex journey. It's now uncertain whether these surface eruptions are delaying the inevitable or hastening it. Beyond Betelgeuse, the implications of Webb's findings are vast. The star offers a rare and invaluable opportunity to study the end-of-life behavior of massive stars up close. These stars are the cosmic forges where heavy elements like oxygen, carbon, and iron are created, substances essential for life, planets, and moons. If Betelgeuse were to go supernova in our lifetime, it would be a historic event, lighting the sky with a brightness rivaling the moon for weeks. But more importantly, it would allow astronomers to capture real-time data on the precise mechanics of stellar death, something never before observed so clearly within our galaxy. Such insights could revolutionize our understanding of stellar physics, element formation, and the creation of black holes and neutron stars. Even if Betelgeuse does not explode soon, the revelations already uncovered by Webb are revolutionary. They mark the start of a new chapter in astronomy, one where we see stars not as static, dying embers, but as complex active systems undergoing prolonged transformation. Webb's ability to observe phenomena in the distant reaches of space, ranging from newborn stars to planets that could potentially harbor life, proves its unmatched power. Its detailed look at Betelgeuse underscores this potential, offering a more complete view of stellar change and complexity. The discovery of the vast dust and gas clouds surrounding the star, expelled in episodic bursts, opens a window into the processes shaping interstellar environments. These ejected particles influence their surroundings, sometimes even triggering the birth of new stars. Studying this interaction in real time helps scientists better understand how dying stars can also sow the seeds of new celestial life. So the question remains, is Betelgeuse truly nearing its end, or is this period of chaos a transitional phase we have yet to fully recognize? Its unpredictability is part of its allure, drawing astronomers back again and again. For over 40 years, researchers have tracked its fluctuating brightness and theorized about its ultimate fate. Now, with Webb's unmatched clarity, the story is becoming more vivid and more complex. What we're seeing isn't simply a countdown to destruction, but a nuanced evolution. The telescope has revealed a star in flux, full of convective turbulence, bright spots, and unexpected mass ejections, evidence that the end of a star's life is less of a singular event and more of an extended transformation driven by forces still being deciphered. Betelgeuse's dramatic dimming, once thought to signal an imminent supernova, now appears less conclusive. Rather than a final warning, it may have been part of a series of surface-level shifts caused by deep internal processes like convection or magnetic interactions. Webb's real-time data has exposed the limitations of our existing models, which long suggested a predictable sequence of stellar decline. Instead, Betelgeuse is teaching us that red supergiants may not follow a tidy script. Its life story is one of chaos and surprise, a challenge to astronomers to rethink long-held assumptions and adapt to new evidence. Webb's observations are prompting scientists to study not just surface phenomena but also the internal dynamics of the star. Fluctuations in brightness may correspond to gigantic convective bubbles rising from Betelgeuse's core, each potentially as large as our solar system. These structures could significantly influence the star's stability and the timing of a supernova. Additionally, Webb has revealed both symmetrical and asymmetrical shells of gas around the star, some ancient, drifting slowly, others recently ejected. These layers suggest Betelgeuse may be entering an undocumented stage of instability. Researchers are now exploring what controls the timing and nature of these ejections and how they affect a star's final collapse. This work also has profound implications for the broader study of supernovae. Most such events are observed in distant galaxies and only after they've already happened. Betelgeuse, due to its proximity and the telescope's incredible precision, offers a rare chance to monitor the prelude to an explosion in real time. It's like watching the climactic scene of a cosmic play unfold, with an ending that could arrive tomorrow, a century from now, or even a millennium in the future, but whose build-up teaches us lessons we could never simulate. If Betelgeuse were to explode within our lifetimes, it would be the first supernova visible to the naked eye in more than 400 years. The last occurred in 1604, observed by astronomers such as Johannes Kepler, though they lacked the tools we now possess. With Webb, an explosion of Betelgeuse would be captured in exquisite detail across the full electromagnetic spectrum, providing an unprecedented view into one of the universe's most violent and generative processes. Even in its current state, Betelgeuse is forcing scientists to rethink cosmic timelines. Stars are no longer perceived as stable, passive objects that quietly collapse at the end. Instead, they are vibrant, dynamic entities undergoing extended episodes of upheaval and transformation. The concept of a living star, one that pulses, changes, and interacts with its environment, has become scientifically valid, not merely poetic. Webb's capabilities allow astronomers to measure temperature variations, analyze the molecular makeup of gases, and track their motion with unprecedented accuracy. Every flicker of light, every swirl of dust becomes a data point in a much larger story about how the universe evolves. Public interest in Betelgeuse's strange behavior has been immense, not because it poses a danger, but because it reminds us of nature's grandeur and the powerful forces shaping our existence. In a world often distracted by the everyday, the sight of a shimmering red star on Orion's shoulder offers a moment of cosmic connection. It recalls humanity's ancient fascination with the skies and carries us into a shared future where, with the help of instruments like the James Webb Space Telescope, we can continue to unravel the universe's secrets, guided not only by curiosity, but by a growing capacity to listen and learn from the stars themselves.